Math and Beats. All right, this video, we're going to look at a topic, a technique, really, called logarithmic differentiation, and we're going to see why this is also can be useful in many circumstances. So let's see. What we're going to do is we're just going to start by considering this function here. Y is x to the x power. And let's assume x is positive for the sake of this discussion. So that's a function we haven't seen in this discussion so far. And we should note that this function is neither exponential nor is it a power function. We do not have the variable x raised to a real number exponent, say n. We do not have a real number constant base, say b, bigger than 0, not 1, to some power of x. So it's kind of a interesting function in which it's neither exponential nor power, but it kind of has some of those properties simultaneously. Now, just so we see that this function is what it is, here's a graph of it. This is the graph of the function x to the x. And as we can see, for positive x values, this function is indeed positive, and it sure appears to be nice and smooth. So you could probably guess what we'd like to do, and that is, let's go ahead and discuss what the slope of this function is. Could we find dy dx for this function? And indeed, that's what we're after. So the goal is, of course, like we just said, we're going to find the derivative of this function with respect to x. How so, though? Can't use power rule. Can't use the derivative of an exponential function rule that we've already established. So what are we going to do? Well, like I said earlier, because we're assuming that the values of x here are positive, then when I raise whatever that positive number is to another positive number, it's also going to be positive. In other words, x to the x here is positive. And for that reason, I can take the natural logarithm of both sides of that equation, y is equal to x to the x, and get that the natural log of y is equal to the natural log of x to the x, right? So up here, this is how it happened. Took the natural log of both sides of that equation. And then what I did was I applied the property that a logarithm of some number to another power, well, that power comes out in front as a coefficient, right? That's a property of logarithms. Now, I'm just taking the natural log, but you can imagine that this might work similarly if I took another logarithm of a different base. So that's where we're at. We got the natural log of y is x to the x. Now we can go about our business because now it's in a form that we know what to do. And so what I'm going to go ahead and do is apply implicit differentiation here to both sides of the equation. And that is take the derivative with respect to x of the natural log of y on the left-hand side. And that should be equal to the derivative with respect to x of the right-hand side, which is x times the natural logarithm of x. Applying differentiation, remember keeping in mind that here y is a function of x. Well then, when I differentiate the left-hand side with respect to x, that is a chain rule situation. Got to take the derivative of the inner function, dy dx, and multiply it with the derivative of the outer function, 1 over the inner function. The right-hand side here, that's just obtained by applying the product rule to x times the natural log of x. The derivative of x is 1 times the natural log of x gives me the natural log of x. And the derivative of the natural log of x is 1 over x multiplied by x gives me 1. So that's where the right-hand side is coming from, product rule. From here, I can multiply both sides of that equation by y, and I get my dy dx isolated. And so because we know from the get-go that y is x to the x, strictly in terms of x here, I'm going to go ahead and rewrite my y, right, bam, in terms of x so that my derivative is strictly also in terms of x. And hence, in this situation, we get the slope of this function x to the x for positive values of x is the function itself, x to the x times the quantity natural log of x plus 1. So we found it. And in fact, what we just did was an example of the process of logarithmic differentiation. And so we can generalize this. The process of this logarithmic differentiation, as we say, given a function, whatever it may be, say y is equal to f of x. And if we're assuming that the function is positive, because we've got to take logarithms of it, so we got to say that, then what do? Well, like in that last example, I'm going to go ahead and take the natural logarithm of both sides of the equation, giving us this result right here. The natural log of y is equal to the natural log of whatever that function of x is. Now again, it does not have to be the natural logarithm. It can be any other logarithm with a base that defines it. However, the natural logarithm seems to have nicer properties in the sense that its derivative doesn't have that extra natural log of the base sitting around, since the natural log of e, of course, is 1. So we just use the natural logarithm as a default for the base, just because it's conventionally more easy to deal with. But anyways, you get the function that's positive. You take the natural logarithm of both sides and apply the properties of logarithms as well, which I'll remind you of here in a moment. After you've done that and applied the properties of logarithms, we then apply implicit differentiation to the resulting equation, whatever that might be. And then, part of this process of applying the implicit differentiation is, of course, isolating the dy dx. The only new thing is that because we can, we're always going to write it in terms of x strictly. So that's the process. And just because, we do it. And now, you might be wondering, why would I do this? What's the purpose of going through this? Well, we saw through that example, x to the x. What other rule are you going to use? First of all, we had to use this process. But they don't have to have a, funky function like x to the x in order to have this process be useful. In fact, as we can see in the statement that's on the screen, if you have a function that's kind of just, very involved, and it has some kind of combinations of products, quotients, and or powers, this process can also be useful. It's a way of getting around a huge mess of product rule and quotient rule and whatnot, as we're going to see through an example here in this video. Now, because we have to use these properties of logarithms within our process, just want to quickly remind ourselves of these. If you have two numbers, say x and y, and they're positive real numbers, and a constant, real constant c here, then remember these properties. The logarithm of base b of a product x times y is the logarithm of base b of x plus the logarithm of base b of y, right? The product is sum rule. We have also in part II here, logarithm of base b of a quotient x divided by y is the logarithm of base b of x minus the logarithm of base b of y. That's that quotient to difference rule. And finally, if you have a logarithm of base b of some number x to the power of c here, then like we saw in that previous example, that's that power rule for logarithms in which the power becomes the coefficient. So just reminding us of these rules because we'll need to use them in the upcoming example here. So let's do that example. Here it is. Let's find the derivative of y with respect to x for this function. Y is f of x is this monster looking thing right here. Boy, oh boy. What is that? That's 2 to the x times the quantity x to the 4th plus 9, all squared, and all of that divided by the square root of x squared plus 4. Now, prior to this video, if you're following along in order, of course, if we were asked to differentiate that function, that would be a big mess, right? Because we got chain rule, we got product rule, and we got quotient rule. So it would be a big old algebra just thing going on. However, as suggested in a previous statement in this video, this is where logarithmic differentiation can help us have an advantage. And let's see how that works. Okay, so we're going to do that. We're going to apply the process of logarithmic differentiation to find this derivative here. And so remember what we do first. We're going to take the natural log of both sides. Now notice that 2 to the x, always positive. X to the 4th plus 9, always positive. Of course, when I square that, it's also positive. And x squared plus 4, also always positive. So in fact, really, in this case, this function here is positive for all real x. And thus, something to consider because we have to take the natural logarithm of both sides. And we need it to be defined. So that's a good thing. All right, so let's do that. Natural log of y is the natural log of this beast, 2 to the x times x to the 4th plus 9, quantity squared, all over square root x squared plus 4. All that stuff, right? Taking the natural logarithm of that. Now, at this point, we also want to then apply our properties of logarithms to rewrite it as much as we can before we do the differentiation process, because it will make our differentiation a lot more easier to deal with. So let's do that. All right. Notice in the numerator there, we have a product, and a denominator, well, it's the denominator. So I'm going to rewrite this, first of all, in terms of the product and quotient rules as the natural logarithm of 2 to the x plus the natural logarithm of x to the 4th plus 9 quantity squared, and then plus the natural logarithm of the square root of x squared plus 4. Except that last plus should be a minus, of course, because that square root of x squared plus 4 is appearing in the denominator. Now let's go further. Can we do anything else? Well, yeah, we can. There's some powers going on here. Natural logarithm of 2 to the x is the same as x times the natural logarithm of 2. And then we also have a square on the quantity x to the 4th plus 9. So that's going to become a plus natural log of x to the 4th plus 9, but then with that 2 out in front. And then notice that really this quantity right here, that term, that's the same as natural logarithm of x squared plus 4 all to the 1/2 power. So I can actually apply another power property there and write this as minus 1/2 natural logarithm of x squared plus 4. So I exhausted my properties here. I did the power property, I did the product property, and a quotient property. There's nothing else to do. There's no property for logarithms of sums. And here's where I can finally apply my differentiation step. Okay, remember, all this is natural log of y, right? So now what I'm going to do is go ahead and write d dx both sides, where I'm going to differentiate both sides here with respect to the input variable x. Now on the left-hand side, we know what y is. It's a function of x. So again, that's that chain rule. We're going to be left with a 1 over y times dy dx. And on the right-hand side, the whole point of this is that my differentiation now should be a lot easier to deal with. And it is, as we're going to see. The derivative of x times the natural log of 2, well, that's just the natural log of 2. Right? Because it's just linear. And then I have a plus of 2 times the natural log of x to the 4th plus 9th. So when I differentiate that, that's a chain rule. The derivative of x to the 4th plus 9th is just 4x cubed. So I have a 2 times a 4x cubed here. And then over x to the 4th plus 9th. Right? It's chain rule. Similarly, in the last term, the derivative of negative 1/2 ln of x squared plus 4. Derivative of the inner function is 2x. So I got a 1 over 2 times a 2x. And then over that inner function, x squared plus 4. let's clean that right-hand side up real quick. We got the natural log of 2 plus an 8x cubed over x to the 4th plus 9. And then minus those 2's cancel, so minus an x over x squared plus 4. Finally, we're going to isolate our dy dx, completing the implicit differentiation step. So we get the dy dx is, well, it's just multiply both sides by y. I get y times the natural log of 2 plus an 8x cubed over x to the 4th plus 9 minus an x over x squared plus 4. And then remember, because we know what y is, right? Y is that original function in terms of x. We go ahead and we finish off our derivative formula. So it's strictly in terms of x here. In other words, we're replacing y in terms of x. So y was 2 to the x times an x to the 4th plus 9 quantity squared all over square root x squared plus 4. And then that y, of course, is getting multiplied by all this stuff, the natural log of 2 plus an 8x cubed over x to the 4th plus 9 minus an x over an x squared plus 4. And there you have it. There is our dy dx. Now, the formula is definitely involved, but you can imagine how much more involved it would be if we didn't apply this process and we did the quotient and product and chain rule all in the same differentiation step. So this helps us bypass all of that and avoids all the messy algebra. It's a little bit cleaner. It's kind of slick. But anyways, that's it. I mean, we talked about the process. We had a function that helped us get motivated to talk about the process. And then we did an example here to end the video. So there's your logarithmic differentiation video. Until next time, it's Math and Beats. Later.